Have you ever just stopped and thought about the hidden world that exists between the code you write and the code your computer actually runs? Yeah, it's this whole space filled with translation and optimization, and today we're going to take a calm peek behind that curtain.
You type out a simple function call, do something call, probably thousands of times, and it just works. It feels instant, right? Almost automatic. But what's actually going on under the hood to make that one little line spring to life? It's a way deeper question than you might think.
All right, so let's dive into the supposed magic. When we call a procedure or a function, it totally feels like we're just giving a direct command, and boom, we get a result. But that's a really clever illusion.
What's really happening is less of an order and more like a carefully structured conversation. The part of your code making the call, we'll call it the caller, and the function being called the callee, they have to follow this very specific protocol. And the moderator for this whole chat, that's the compiler.
Think of the compiler as this master translator. Its whole job is to take your high-level language, like C++ or Python, and turn it into the raw machine code that the processor actually gets. But here's the thing, translating directly is incredibly hard and super rigid. It'd be like trying to translate a complex novel word for word into another language. You'd lose all the nuance, all the meaning. Well, the compiler faces a very similar problem.
So, to solve this, the compiler uses a secret language, a middle step. It's called an intermediate representation, or IR for short. You can just think of it as a blueprint. It captures the real essence of your code in a format that's just much easier to work with, to analyze, and eventually to translate into super efficient machine code.
When a compiler first looks at your code, it doesn't just see lines of text like we do. It builds this structure, called a syntax tree, which maps out the whole logical hierarchy of what you wrote. Like in this example, you can see how a simple assignment is broken down into its basic parts. There's an array access, an addition. This tree is really the first step for the compiler to understand what your code actually means.
And this tree? It's packed with useful info about the relationships in your code, but it's also a bit unwieldy. Trying to generate efficient step-by-step machine instructions straight from this complex branching thing is a huge challenge.
And this leads us to a really pivotal moment. The compiler takes that complex tree and just flattens it. It turns it into a simple, linear sequence of instructions. And that sequence is the intermediate code. It's kind of like taking a complicated sentence diagram and turning it into a series of simple, one-thing-at-a-time statements.
So why even bother with this middleman, right? Well, there are three huge reasons. First, simplicity. Each little instruction in the IR does one and only one tiny thing, super easy to understand. Second, that simplicity makes it way easier to optimize the code. You can spot stuff to cut out or rearrange to make it faster. And third, portability. This is a big one. If you have, say, 10 languages and 10 types of machines, you don't need to write 100 different translators. You just write 10 translators to the IR and 10 translators from the IR. That's 20 components, not 100. It saves a massive amount of work.
So if the whole goal is a simple, linear list of instructions, what does that actually look like?
Well, one of the most common and honestly most elegant forms is called three-address code. I know the name sounds a bit technical, but the idea behind it is just beautifully simple, and it's the foundation for a ton of how compilers work today.
The core principle, its real power, is just how simple it is. Every single instruction has, at most, 3 parts, or addresses. 2 for the inputs, the operands, and 1 for the result. And you only get one operator, like a plus or minus, on the right side. That's it. Every complex thing you write gets broken down into these little bite-sized pieces.
Okay, let's make this totally concrete. Check out this single line of code, a of I equals b plus c times 2. In three-address code, that becomes a series of steps. Notice how the compiler just invents these temporary variables, t1 and t2, to hold the results along the way. First, it calculates c times 2 and sticks that in t1. Then it adds b to t1 and puts that result in t2. And finally, it takes the value from t2 and assigns it to the array element a of I. See? One complex step becomes 3 simple, totally unambiguous ones.
All right, now that we get this simple blueprint, let's go all the way back to our original mystery. What really happens when you call a function?
And this brings us to the key insight. A function call isn't a single instruction in three-address code. It just can't be. Instead, it's a protocol, a standardized sequence of simple steps that both the caller and the callee have agreed to follow. It's the script for their whole conversation.
This slide just lays it all out beautifully. Let's walk through the call n equals f of r AI. So, step 1, the caller has to prepare the argument. It figures out the memory address for AI and puts its value into a temporary variable, let's call it t2. Step 2, it formally says, hey, this t2 is a parameter for the call I'm about to make, using a param instruction. Step 3, now it makes the actual call. The call f1 instruction jumps over to the function f and tells it, by the way, expect one parameter. Once f is all done, its return value gets put in another temporary variable, t3, and finally, step 4, the caller takes that return value from t3 and assigns it to n. It's this perfect 4-step dance.
So, as we've seen, this whole process, it isn't some unknowable magical force. It's really all about breaking down something complex into simple, manageable pieces.
What feels so instantaneous and magical when we write our code is, in reality, this elegant and highly predictable system. Every single function call you write follows this exact protocol, translated into these discrete little steps. And understanding this really matters. It's this systematic approach that allows our programs to run so reliably, and it helps explain why a tiny change in your code can sometimes have such a big impact on performance.
And this really gets to the very heart of compiler design. It's this beautiful balancing act. It's all about finding the right models, like 3-address code, that are simple enough for us to reason about and optimize, but still powerful enough to express any program you could ever dream of writing.
So the next time you write a function call, maybe you'll think of this. You're not just giving a command. You're kicking off a quiet, orderly conversation, one that the compiler has carefully scripted in its own secret language, turning your complex ideas into pure, elegant simplicity.